Professor, you're muted.
Yeah, thank you. I noticed just now. All right. And yeah, this is exactly what happened. One of the panelists left and ended the meeting for all of us. And I mentioned several times already, asking, begging the panelists not to do that. There's no way we can technically prevent it because we have to make panelists co-hosts, but their co-host gets the power to end the meeting for all. And we asked people not to do it. All right, so it is becoming pretty disruptive for the lecture. Okay, so please, if it keeps going on like that, we just stop doing panelists. Okay, I just don't see any other way. And Cheyenne, even, do you read emails from Cheyenne? She added even, a paragraph saying, please do not end the meeting for all. Just leave the meeting if you no longer want to be here, but do not end it for all if you're a panelist. So please observe this, all right? It's getting, honestly pretty annoying. All right. But of course, if someone wants to teach this class instead of me, I wouldn't mind. Yeah, maybe one of the people who's getting an A. Well, there are many people who are going to be getting an A, so we have a good choice here. Yeah, and good point. Panelists are really expected to stay all the way through and not leave, halfway through. Well, not halfway, but still 40 minutes before the end of the lecture. All right, so we are back, hopefully. Sorry about that. I wasn't. It was pretty unexpected. All right, and we were talking about their ID stage, right? Where we read IFID and we read register file and we write into their IDEX, right? And IDEX would need to contain all the information needed for this instruction for all the subsequent stages. So it's not just their their extended immediate field, and it's not just their instruction word, but it is, for example, also both values read from their register file, right? Because we might need to do something with those values, add them or subtract them, and we should serve those values then to the ALU, and that means that we have to save them in our buffer register. Okay, and yeah, I know that person won't even know what they did because they left. Well, hopefully they have friends who tell them. I don't even know what that person is. I don't think I can I can determine this, unfortunately. Otherwise I would just reach out to that person individually with with my little request not to do it anymore. All right, so here is the execution stage. Again, it's very similar. We read this IDEX register, we do our multiplexer ALU thing, and we write into EXMEM. So ALU is used for this instruction. What does ALU do at this stage? Someone, please. Well, it is a LW instruction. ALU computes the effective address that will be then used to access data memory. Okay, and it's not a branch instruction. That's why you see this shift left 2 and this adder, they are not, they do not have this blue background, which means they're not used for this instruction, right? Because it's not a branch instruction. All right, so this is just to help you understand the notation used in this in those diagrams, and hopefully those diagrams now really talk to you, and they make sense. So mem, it's an LW. That's why memory is read, right? So we load from memory into then register, and as usual we read ex mem register buffer, and we will write the result of this stage of this mem stage for this instruction into the mem WB register for our instruction, right? So of our thing. All right. So then WB, that's an interesting one. So let me. Okay. So here it looks like it's the same. We read from mem WB register, and then we write the value that was read from memory back into right. So it would be this value read, and that we stored in memwb. Now we read it from memwb, and we are writing back to the register file. Okay, is that making sense? Yes, no, maybe? How many people do we have? Do we have? Oh, we have 64 people. So, can you access can you access chat, or doesn't, or it just no one knows the answer and has no guesses? Oh, my bad. I didn't scroll. Yeah. All right. So yeah, you can. Were there any suggestions? So people are saying, yeah, makes sense. Okay, cool. Although that is not the correct answer. So the correct answer should be, it's not. Well, it's making sense, but there's an error here. Can someone point out what the error is in this diagram? Yes, but won't there be data hazard if it's pipelining? Exactly. This WB is broken because we are writing back the value. So the right data here is going to be the correct value that LW read from the memory, but it's going to be writing back to the register that is determined by the instruction two instructions ahead. So there's LW and then something, and so we are here at the WB stage, right? So next instruction would be at the mem stage, and next instruction would be at the ALU stage, and next instruction, oops, not ALU, we call it EX, and next instruction would be at ID stage, right? So whatever that instruction is, and here we have this instruction. Let's say T1, T2, T3. Okay, and so the right register that determines into which register stuff is written will be coming from this instruction, right? Because this is our ID stage, right? If we break it into stages like that, so this is EX, this is MEM, okay, up to here, and this is our write back. So this instruction at ID stage is this add instruction that has T3, so this write register would be T3, okay, and not the register that was here in the LW instruction. Okay, it's gonna write to their own register. All right, because we messed up this. Well, no, it was intentional, of course. So no, it's not bubble. We just need to fix the error. It's the flaw in our design. So this design is flawed. We can fix it. Okay. So how do we fix it? Any thoughts?
I have an idea.
Yeah, go ahead.
Maybe so like the instruction is pointing to the right register. So maybe instead of doing that, it would just like go through all the uh maybe it'll go straight to like. Actually, I'm not too sure. I think it just it just skips every step. It just doesn't connect the instruction to write register, and then it will somehow come back and then write to write register. I don't know how
Exactly.
to do that.
You spotted the problem exactly correct. So the problem is in this. So everything related to our LW instruction is in this register at this moment of time, right? And if the write register is not here, it's lost. There's no way for this instruction to remember that it was supposed to write into S0. So the solution is, well, we need to carry this this destination register, this S0, with the instruction, so that when it needs to write back, we can sort of do this, instead of just this being write register, we can do something more fancy. We can have a multiplexer which is saying, well, what is this write register? Is this the one coming from the instruction word, or is this the one coming from our write back stage? Okay, and we make this this multiplexer. Okay, but the key is we have to change our buffers, to extend our buffers, so that this value is stored, because if that value is not stored, there's no way we can recover it. Of course, we cannot read the instruction again. It wouldn't make any sense, right? The instruction was read, and we just lost some essential information about this instruction along the way, and we just want to prevent this. Okay, so this is exactly their solution. Where are we? Oops. All right. So this is their, their not too formally, but this is kind of the sketch of, oh, okay, so from this instruction word, right, we need to kind of, in addition to keep their information about their write register, right, and kind of keep it throughout their the rest of their cycle, of the execution cycle, so that if turns out that we need it, we need to write the register. We know which register to write to. So and it's a sketch. So in if we do it like that, we don't even need a multiplexer, right? So we can come up with a simpler design, right? But this solves this problem, okay? Because now we have we always store the write register. So instead of multiplexer that makes this decision, which thing to route, we just say, all right, we're just gonna keep this write register in the buffers, for all remaining 4 stages of the execution. So in all 3 buffers, there will be this little section, five bits, that stores the write register. Whether we need it or not, for some instructions we might, for some instructions we might not, but we have it just in case. And for instructions where for which we need it, it's gonna come very handy. So the register to write to does not come out of the register's box. It comes out of their instruction word, okay, because it is encoded in the instruction itself. Remember those RS, RT, RD stuff? All right. So that was LW instruction. So just to realize what we've done. So we looked at a single instruction, and we had a snapshot of the processor at each stage. So it was one cycle at a time: first cycle, second cycle, third cycle, fourth, and fifth. All right, all 5 cycles, one cycle at a time, that show how our load instruction would go through the entire pipeline, from the time when it entered the pipeline, when we fetched this instruction here, to the time when it left the pipeline here, when it is done and the instruction is pushed out of the pipeline. And the same stuff for another instruction store. So it's SW. The first 2 stages are going to be the same. So we are not showing them because they're exactly the same, IF and ID. The X stage is is the same, I believe, but they still show it, right? Because we read their buffer, then we compute the address, the effective address for the memory, store it in their memory, in the buffer, ex mem buffer, and then this stage is clearly different because for store W we write to the data memory. So see how this left half of data memory is shaded because we are writing to that data memory. And then write back is also different. In write back, we don't have to do anything for store W because there's just no work to do, right? We are writing from the register into the data memory, so no registers to write. And the multi-cycle pipeline diagram, right, is just a different view. We can do the same stuff with the instructions, but we show each clock cycle. Right, CC stands for clock cycle. Multiple clock cycles on the same diagram. So this is essentially our time dimension, and this is our program. So instructions execute from top to bottom, and we show in for each instruction which resources it uses, using the same notation that we did in the single cycle diagram. So LW, when it reads instruction memory at their, so this would be their for this instruction it would be the IF stage. It reads instruction memory and writes to their buffer, and then next clock cycle it reads from the buffer and reads from the registers and writes to their next buffer, and then CC3 it reads from this buffer, uses ALU, writes to this buffer, and so forth. So you can see how the instruction enters and leaves their pipeline in a more compact way in just a single diagram that shows pretty much the part of the entire program. Okay, so again, the notation is when we are writing, it's the left part that is shaded. So LW writes to the register file. This is the WB phase, and when we read something, then we we highlight the right part, the right half of their memory. So instruction memory, we only read, and that's why we only would have their right part of their IM highlighted. Whereas data memory, you see, for load word, we read, and for write, for store word, well, it's not here, so we don't do anything. And yeah, so that's and I think yeah, there's a mistake, right? See how they actually, this one was supposed to be with the right half highlighted, not this one. This is wrong, right? This should be add instruction doesn't access data memory, right? So this should be all white background, and instead this should have right half highlighted in blue. So it's clearly a a little mistake. And the dashed thing here, right? So see how this is dashed? It means this unique case for the register file where it only takes 1/2 of our clock cycle to read or write, and that's why we see that we've seen before that we can read and write at the same time, and that's why when we are reading in the second half of the cycle, right? So if we plot it here, it would be like if we have to do the register read, it happens here, and when we do register write, it happens here, right? Like for well, for different instructions, right? So this is for this instruction, and this is for this instruction. Okay, so this is the notation, and so this is a slightly simplified form. Again, same multi-cycle diagram, but slightly simplified so that we less fancy. And this is what you will need to do on the homework, right? Except for even easier, instead of spelling out all words, you can just do abbreviations. All right. Well, let's do one quiz at least. So, yeah, I was hoping we would get more accomplished today, but it is what it is. So, how many cycles in total for this entire program would it take to complete? So, count from their time this first instruction enters the pipeline until the last instruction leaves the pipeline. Is there going to be a quiz for the extra credit question? No, that's not going to be a quiz because all questions on the test are the same number of points. So you can think of any single question of being extra credit. All right, it doesn't matter which one you nominate because the result is going to be the same. So pick your favorite or pick your least favorite question and think of it as extra credit. They're all worth 25 points. All right. So let's cover this. We have about 1 minute left, and then next time we're going to restart with the control. So this single cycle pipeline diagram is exactly similar to the ones that we've seen. It's a snapshot, but now it shows not just one instruction, right, which would be not unrealistic, but the entire state of their processor at any given moment of time, which means that this instruction is just being fetched, right? It is at its IF stage, whereas the previous instruction, this one, is at the ID stage, and the previous instruction is at the execution stage. So if you trace it back to the previous example, right? LW was first, sub second, add third, LW, and then the other add, right? So you see how they are positioned. LW is almost done. It is about to leave the pipeline, whereas add is just entering the pipeline, and it is being staged at this cycle. So again, single cycle diagram means a snapshot, means a given cycle, a given moment of time. And here, so we're just showing, which instruction is occupying or is using which resources of this pipeline. And it is 150, so slide 83. And next time we will start with the pipeline control, so adding more fun with all the control signals, but that's coming up on Tuesday before the Thanksgiving. And with that, let me wish you a good, well, not holidays yet, a good weekend. Enjoy your weekend. Enjoy, some sunny weather. And please, connect to us on Tuesday. Even if you're leaving for the Thanksgiving, please come to our lecture. And I'm really looking forward to it. Thank you, folks. Have a good day.